Here we go with the opener to this section. If a mysterious man comes up to you on the last day of school and says, I need you to wash cars every single day for 30 days straight during the summer, I'll pay you good money. You ask him how much. He responds, whatever you want.
$100.
You say $1 million.
No, I say
He stops and thinks and says, sure, I can give you the million, but how about instead of $1 million, I give you a penny right now. And the first day of work, I'll double it and give you 2 cents. And the second day of work, I will double that and give you 4 cents. And each day, I'll keep doubling the previous day for 30 days straight. What do you think?
No.
So I want you guys, okay, so here are the two options. You take the million up front, or you take 2 cents on the first day of work, right? It says right here, day 1, 2 cents. Day 2, 4 cents, it doubles. Day 3, it doubles, 8 cents. Day 4, it doubles, 6 cents. So I'm going to give you guys a couple of minutes. If you're watching this for the first time on video, hit pause right now and let everybody partner up and discuss it for a good minute or two. Use a calculator, guys, but I need some type of, not just a guess, so I'm guessing a million's better, or I'm guessing doubling a penny's better. Get a calculator, get some real numbers. Let's see what you got. A couple of minutes. Go for it. Okay, so I appreciate you guys actually trying to figure this out. I know some of us already got it, and I have it actually drawn out for you so you could actually see. Okay, on day one of work, you get 2 cents. The second day it doubles 4 cents, it doubles 8 cents, it doubles 16 cents. What's 16 times 2? 32. And then times 2 is 64. Then you finally get to $1.28. Check it out, guys. After 7 days of work, you only get paid $1.28 for that entire 7th day. That sounds pretty horrible, right? As we continue on, day 8 is $2.56. Day 9 is $5. Day 10, day 11, day 12. Finally, by day 12, you're making at least some decent money. You get $40 for that entire 12th day of work. But if you keep doubling it each day as you go, $81, $163, $327. Day 16, you got $655. Day 17, $1,300. Day 18, $2,000. Day 19, $5,000. Day 20, $10,000. Day 21, $20,000. $41,000, $83,000, $167,000. Over $250,000, then you're over $500,000 by day 26. By day 27, on the 27th day, you do get paid over $1 million just for that 27th day. And you keep doubling it. The 28th day, you get $2.5 million, over $2.5 million. 29th day, $5 million. 30th day is over $10 million. And not only that, guys, you'd have to add up all these days to find out how much you really would have made. Okay? So I gave you this example, it's not a real situation because no one's going to offer you $1 million or yet alone $20 million to wash cars for a month. But I gave you this example to demonstrate how an exponential growth function at the beginning, 2 cents, 4 cents, 8 cents, it seems like it's not growing at all. But then as you continue on with time, you'll see that it grows drastically. It grows crazy. It grows exponentially. So let me actually demonstrate the name of this. It's called an exponential growth function. And do you guys remember functions? You plug in an input, you get out an output. You guys remember that? We'll go over it in a couple of minutes. But right now, let me just show you this exponential growth function. It's y equals 2 to the x power. And I hope you guys remember that the x values are the inputs and the y values are the outputs, right? So when I do plug, like let's say I wanted to find out, okay, my first day, what happens? Well, plug in 1 into the x. What's 2 to the 1? It's just 2. Your second day, what do? Plug in 2 into the x. The inputs are the x's. 2 to the second, that's 4. That's how you get 4 cents. What happens on the 5th day? Well, plug in 5, 2 to the 5th, and you'll get 2 times 2 times 2, 5 times you get 32, right? So this is the function that actually models this situation. This is the easiest type, I think, the easiest type of exponential growth function that we're going to begin with on the notes today. Let's jump to our notes. And here are the notes. And let's just start with the first part of the notes of vocabulary. We're going to be graphing exponential growth functions. And what we just saw previously was an exponential growth function, y equals 2 to the x. And we saw that you started out with pennies, and then all of a sudden it kept growing and growing to millions of dollars by the end of the 30th day, right? Over 10 million. Anyhow, let's review some main vocab words. Domain. We should all know what the domain and the range is. I don't know if you guys remember this when we first went over functions. You guys remember the function machine?
Yeah.
Yeah? And whatever you put in here is called the domain. Whatever you put in here is called the inputs, right? You're putting it in, inputs. And they're also known as the x values. For example, something that we're comfortable with, something that we're used to from a while back, y equals 2 to the x plus 1 if you want. Like you could plug in a 5 and it'll come out as what? As an 11, right? You could take the 5 and plug it in here, and you're going to plug it into the x's. 2 times 5 is 10, plus 1 is 11. That'll be your y value. So the input 5 gave us the output 11. The input 5 gave us the output 11. The x value of 5, when you plug it into x, it gave us the y value of 11, the y value. So x values are going in, y values are coming out. And also you need to remember that domain are simply the x values, the inputs, and the range are simply the outputs, the y values. And how could you remember that? Way back when I told you domain alphabetically comes first, range alphabetically comes second. So the domain is what goes in, the range is what comes out. I hope we remember that. Let's go back to the notes over here. A parent graph is a function without a, h, or k. Okay, so I know you're thinking, what the heck does that mean? We need to get familiar or comfortable with this form right here. Y equals, this is going to be a certain number, and maybe it's not a number, maybe it's just 1, right? And then b is another number, and it's going to be to the power of x minus h, and then plus k. The a, the b, the h, and the k, they're all numbers, and the y and x stay y and x, okay? Now, I'll be honest with you. The h, we're not going to use it on this section in Algebra 1, but you do use h in Algebra 2. Okay, so I just wanted to put it there because you're going to be using it in Algebra 2, not in Algebra 1. But we will have a k value, okay? A couple other things. The h value in Algebra 2, you will see that whatever you have here is going to end up shifting your parent graph either left or right. And the k value that we are going to be using in this class will be shifting your graph either up or down. So if you have a plus 3, your parent graph will get shifted 3 units up. If you have a minus 5, your parent graph is going to get shifted 5 units down. So I know that this is kind of weird, but it'll make sense in a couple of moments when we actually start graphing. But anyway, let's talk about, or let's continue reading here. An exponential growth function has a form of this, all right? The simplest type of exponential growth function is y equals b to the x. So without the a, without the h or the k, this is the easiest. And we just did a really easy one, y equals 2 to the x. We saw that guy giving us a penny and then doubling it and doubling it and doubling it. So right now, let's not use that situation. Let's just look at the function y equals 2 to the x and let's graph it, okay? The way we used to graph any type of function using an xy table. So everybody, please, in this area, go ahead and jot down xy. And we need some inputs and we need some outputs, right? This is what I highly recommend on this whole section, all of next week, or this whole section, however long it takes us to cover. I want you guys to use consecutive integer inputs, nice numbers, and let's start with 0, but I'm not going to put the 0 up here. I want to put the 0 somewhere in the middle, all right? Because I want to begin with 0 and then continue on with 1, 2, 3, maybe 4, it depends, right? And I also want to show the negative side, -1, -2, -3. Now, I've always said on any XY table, you could plug in any values you want. You could plug in 5, you could plug in 8, you could plug in -3, but I want you to put the numbers in order. That's why I put 0 right in the middle, 1, 2, 3, 4 this way, and then 0 right in the middle, -1, -2, -3 this way, okay? Now, let's actually plug in the inputs to get out outputs. If I plug in 0 right there, what is 2 to the 0 power? Remember the laws of exponents, the rules of exponents? Anything to the 0 power is what? Equal to 1. Anything to the 0 power equals 1. I hope you remember that. Let's continue on. If I plug in a 1 right in there, what's 2 to the 1 power? That's 2. If I plug in 2, what's 2 squared? 4. And if I plug in 3, what's 2 to the 3rd? 2 times 2 times 2, that's 8, right? And how about if I plug in 4, the input 4 right in there, what's 2 to the 4th? 16, right? And how about backwards, the -1? If I plug in -1 right there, now this might require some thought. going back to the rules of exponents, if I plug in a -1, 2 to the -1, you have to take that whole thing because it's a negative exponent and move it down to the bottom, which means that it becomes a fraction now. There's going to be nothing left up on top and 2 to the 1 on the bottom, which is really 1/2. You guys remember that? So this becomes 1/2. And then if I plugged in a -2 right here, 2 to the -2, that means it'd have to move down to the bottom. It'd be 1 over 2 to the 2, which would be 1 over 4. 1 over 4. And then plugging in -3 would give us 1 over 8. I hope you remember this. Now, that sounds confusing, huh? Let me give you right now a shortcut, a great way to come up with these outputs a lot faster. Now, because we used consecutive integer inputs, I didn't go from 1 to 3 or from 1 to -2 to 5. I went nice and in order, 0, 1, 2, 3, 4, and backwards nice in order, -1, -2, -3. Everything's in perfect order. So when you have the inputs in order, you're going to be able to look at the outputs and they're going to have a certain order. Now, what do I mean by that? The base, the B value, the base, actually is called the growth factor because the output is going to grow by this. Now, what do I mean by this? By 2. So let's plug in the easiest number. What's the easiest number to plug in? Out of all the numbers we plugged in, which one was the easiest? 0 was the easiest, right? When you plug in 0, you get the output of 1. Now, instead of plugging in 1 right there and thinking about, oh, 2 to the 1 is 2, I could simply look at this output and say that it's going to grow by the factor of 2. So in other words, 1 times 2 is what? 2. And when I take 2 and multiply it by 2, it's what? 4. If I take 4 and multiply it by 2, it's what? 8. 8 times 2 is what? 16. So I think using consecutive integer inputs, which gives you order on the inputs, which will provide order on the outputs, is a lot easier to just multiply by 2 than thinking, oh, what is 4? What is 2 to the 4th? Okay, 2 times 2 times 2 times 2, right? That's more challenging as opposed to, okay, let's plug in 0, get out a 1, and then this output, let's modify it by 2. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. Do we get it? Now backwards, if I am multiplying by 2 this way, now the reason why I'm multiplying by 2 is because the base is 2. So if the base would have been 3, guess what? Instead of 1 to 2, I'd have a 1 to 3. If this were a 3, I'd have to multiply by 3. 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. If the base was 3. But because it's 2, it's going to be growing by multiplying by 2. So anyways, going backwards, 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. Going backwards, what's happening? Am I multiplying by 2 from 8 to 4? I'm dividing by 2, right? So 8 divided by 2 is 4. 4 divided by 2 is 2. Or instead of saying divided by 2, you could say multiplying by half, which is the same thing as dividing by 2. So when I get to 1, 1 divided by 2 is 1/2. 1/2 times 2, 1/2 times 1/2, which is dividing by 2, is 1/4. Times 1/2 is 1/8. The next one would be 1/16. The next one would be 1/32. Okay? Anyways, I just wanted to give you that little shortcut on coming up with the outputs, and that only happens when you have consecutive integer inputs, when they're in order. Let's actually graph this bad boy right here. So the coordinate 0, 1 is right here. Let's go to the coordinate 1, 2. Where's that? It's 1 on the x, 2 on the y. It's right there. Let's go to the coordinate 2, 4. 2 on the x, 1, 2, 1, 2, 3, 4 is right there. And 3, 8, you're going to go 3 on the x, 8 on the y, it's up here. And now let's look at the negative values for the inputs. -1 and half. Okay, that's a little weird. You're going to go -1 and then halfway up. Okay, let's put a dot at -1 and then half. And then the next one, -2 and 1/4, that's even weirder. You're going to go -2 and then 1/4 of the way up. That's really half of the half. So it's even closer to the x-axis. Half of the half is about right there. And if I go to -3 and 1/8, that's even closer to 0, right? So if I go -3 and 1/8, at this point, it's hard to draw the difference between 1/8 and the next one, which would be negative 1/16, or the next one, which is negative 1/32, it just gets infinitely closer and closer to 0 going this way. But it never actually touches 0. It never actually gets to 0. Okay? This is what we call an asymptote. Okay, an asymptote. Let's go back up here to the vocab word. An asymptote is the line that your graph will infinitely approach but never touch. It'll infinitely approach it but never touch it. And it's going to be the line y equals k. So in this case, k is right here. And in this original graph that we just did, the easiest type, there is no k. That means that k is 0. So our graph, as you could see, from right to left, infinitely approaches the 0 because there is no k. Okay, it takes some time to wrap your mind around this. But anyways, this is the graph. Let me graph it in blue. So from left to right, it looks like it's not growing at all. Kind of like those first couple of days where you got 16 cents, 32 cents, right? But then you start getting to dollars and then doubling those dollars and doubling and keep going. It's going to grow drastically. This is what we call an exponential growth function. Now, what makes it a growth function? That from left to right, it looks like it's not growing much, but then all of a sudden it grows a lot. And technically it could grow in a positive direction or even grow in a negative direction. Okay? Positive direction, we thought about that in the opening problem, that you had pennies and then it grew to millions of dollars. Now, a negative growth, you could think of that like in the way of credit card debt, right? You go to college, you get a bunch of credit cards, and you don't owe any money, but then you start using them and you don't pay it off and you use them more and more, it's going to grow in a negative direction. So growth could be both in a positive direction or in a negative direction. Okay. Another important detail is the growth function, it's going to approach a certain value. In this case, the asymptote y equals 0. Okay, the asymptote y equals 0. So from right to left, it's getting smaller, 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 and it infinitely approaches 0, but never actually touches. Let me help you wrap your mind around that concept. So here we go. Here, record me. Okay, so I wanna walk towards the wall. I wanna take 4 steps, right? So check me out. I'll go 1, 2, 3, 4. Okay, and now I wanna take half of that towards the wall. That's going to be 2 steps. 1, 2. Then I want to take half of that, which is 1 step. 1 step. Then I want to take half of that, which is half a step right here, half of that. And then half of that, and then half of that, and then half of that, half of the half. I end up just doing this. I will never touch the wall. I'll never touch the wall. Okay, and that's the concept of an asymptote. You're getting closer and closer and closer, but you never actually touch it. It just infinitely approaches. Okay, so let's continue on here. I know it's a lot. I apologize. Anyway, let's talk about these other details. The domain of this guy. Domain are the x values. So let me ask you this. Does the function y equals 2 to the x, the domain values, those are the x values. So does this blue exponential growth function, does it have x values in the negative direction? Over here? Doesn't it go this way? No. Yeah. Doesn't it continue to go this way forever? Yeah. So we know that it has the x value of 0, the x value negative 1, negative 2, negative 3, negative 4, negative 10. But it also has that negative 20, negative 50, negative 1,000. It goes on forever in the negative direction. Does this graph exist at the x value of positive 10? Does it exist at the x value of positive 10? Yes. Even though you don't see it on this graph, it looks like it curves up, but it never goes straight up. It always continues to grow this way further. What do I mean by that? You could plug in the input 10 right there, 2 to the 10th power. I think that's like 2,100, I don't know, but it's a big number, right? So if you went up to that value, you'd eventually get to that blue line. So the coordinate 10 and 2,000 something, or is it, what is that? 1,024. Okay, so 10, 1,024 really will be on this blue line. If you're at 10 and 1,024, it does exist. So the domain, when it's asking what are all of your x values of this blue line, the domain is x equals all real numbers. So you could use a symbol, or you could say all real numbers, whatever you like, because it does go in the negative direction on the x's forever, and even though it curves up, it does continue to grow this way forever. Okay, so you could plug in 1,000, you could plug in 1,000,000, you could plug in 1,000,000,000 if you wanted to as a power, and you'd still get out even a way bigger answer. So the domain's easy on all these exponential growth functions. The domain's always going to be all real numbers because it always goes to the left and it always goes to the right forever. Let's look at the range though. The range is a little more interesting. The range are the y values, right? If we look at over here, remember the range or the y values. So when I look at my graph and I think of my y values, which are obviously on the y-axis up and down, does this blue line exist at the y value of 0? It does not. It infinitely approaches, never touches. Does it exist at the y value of 1? Yes. Does it exist at the y value of 2? Yes. Does this graph exist at the y value of -10? Is the blue line down here? No. Is it at -5? No. Is it at -1? No. It's not even at 0, even though it looks like it's at 0. Remember, it never actually touches, it just infinitely approaches. Okay? So it doesn't even exist at 0, but it does exist above 0. Okay? So when I state my range values, I am going to say that y must be greater than 0. I can't even put greater than or equal to, because even though this way it looks like it's going to 0, but it never actually touches, it just infinitely approaches. Remember, right here the y value was 2, half of that was 1, half of that was half of the half is 1/4, half of that is 1/8, half of that's 1/16, half of that's 1/32, 1/64, 1/128. It continues to get super small, but you could never, you're going to continue dividing by 2, so it's going to continue approaching 0. So it infinitely approaches 0, but it never actually touches 0, and that's why the range value is y is greater than 0. Okay, what else? Let's identify the y-intercept. Y-intercept is where your line actually crosses the y-axis. Where does it cross the y-axis? Crosses right here at 1. Thank you very much. And for old times algebra's sake, we would say, how do you find the x-intercept? You set y equal to 0. How do you find the y-intercept? You set x equal to 0. So if you did plug in 0 and you do the math, you get out a 1, well, that's your y-intercept. So the y-intercept is 1, or you could give it as a coordinate 0, 1, whatever you like. The asymptote, again, on our notes above, it says the asymptote is y equals k. But we know that this original graph didn't have a +2 or a -3 or a +1. There was no k, so the k value is 0 in that case. So what is the asymptote of our blue line? It's y equals 0 because the k was 0. There was no k. And that makes total sense because this graph really does approach 0. Approaches, never actually touches. Okay? Let's try a couple more down here. It says, now try and graph both of these and see how the graph changes. So the original parent graph of y equals 2 to the x above, we know how it behaves. It starts off here and it goes up forever. But what happens if your a value, now what is the a value? The a value is that number that's out in front of the base. What if your a value happens to be -1? Right? Or what if your a value is +2? It's going to affect it. So let's check it out. Let's check out how it affects it. And I might as well start giving you the general steps. If you ever do have an h or k, ignore it. Okay? And just look at your y equals a times b to the x. So let's look at that and let's make an xy table. Everybody together, please. XY table, and let's plug in some easy numbers, and let's put 0 in the middle, and you want it to be in consecutive integer order. Why do we want a nice, beautiful, organized input? So we could have a pattern on the output, and that pattern will be the growth factor of 2. Okay? So anyways, let's do consecutive integer input. So if you put 0 in the middle, 1, 2, 3. In the opposite direction, -1, -2, -3. Those inputs are perfectly in order. Okay? So, because they're in order, we're going to be able to use the growth factor because there's going to be a pattern out here on the outputs. Because they're in order, there's going to be a pattern on the outputs. So let's first understand what this really looks like. We have an A value of -1. So I guess it's really necessary to rewrite it with the A value being clear to you. So let me rewrite it as y equals -1 times 2 to the x. Okay? That way we could see that the A value is the number that's being multiplied by your base out here in the front. So your base is not -2, even though it looks like the base is -2. Your base is really 2, and there's a multiplication of -1 in front of it. Remember, this negative sign does not belong to the 2 because there's no parentheses around it. If you had parentheses around it and then to the x power, yeah, it's -2 as your base. But right here, there are no parentheses, so that means that the negative is out in front. You're going to do exponents first, so it's really 2 to the x with the A value of -1. Anyhow, let's start plugging in some numbers and pulling out some answers. When I plug in 0, right in here, 2 to the 0 is 1, and then 1 times -1 is -1. So when I plug in 0, I get out a -1. Make sense? When I plug in a 1, let's plug in a 1 right there. What's 2 to the 1? It's 2. And then 2 times -1, that's -2. So I get out a -2 as an output for the input of 1. Now, if I plug in 2, that'll be what? 2 squared is what? 4, and 4 times -1, -4. So as you can see, it's pretty easy to do this, but there's a shortcut. That shortcut I showed you previously. If these are in order, then you could plug in the easiest one, 0. Plug in 0, get 1 times -1, you get -1 as the answer. And then you could use your growth factor, which is 2. The base is your growth factor. So you could use 2 to get to the next output. So here's the first output. To get to the next output, all you have to do is multiply it by 2, and you get -2. Multiply it by 2, and you get what? -4. Multiply it by 2, what would the next one be? -8. And the next one after that? -16. So you see how easy it is to come up with the inputs and outputs if your inputs are in order? Okay. Now let's go backwards. If from here to here it's multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2, backwards is really multiplying by half, right? Half of 16 is 8. Half of that is 4. Half of that's -2. Half of that's -1. What's half of -1? What's half of -1? -half. What's half of that? -1/4. What's half of that? -1/8. Right? We keep multiplying by half. So we will do this enough times that you'll get comfortable with the inputs and outputs. Now let's graph the 0, -1. 0, -1 is right here. Let's graph 1, -2. It's right here. Let's graph 3, -8. 3, wait a minute, I messed up. 2, -4 is what I need to graph. 1, 2, -1, 2, 3, 4. I'm sorry. And 3, -8 is way down here. Now let's go in the negative direction, -1, -half. So if you're at the origin and you go -1 and then you go -half, halfway down, you'll be right there. Halfway. And then half of that would be 1/4, and half of that's 1/8, half of that's 1/16, 1 over 32, 1 over 64, 1 over 128, 1 over 256. It's getting smaller and smaller, approaching 0, but we know that it never actually touches 0, just infinitely approaches. So anyhow, we have our graph. There was no H or K shift, so we don't need to shift these points anywhere. Anyhow, let me just graph it. And you put an arrow, and you put an arrow. And now we should be able to identify certain things. What's the domain of this blue exponential growth function that's going in a negative direction? Does it go to the left forever? Yes. Does it go to the right forever? It looks like it doesn't, right? It looks like it curves down, and at some point it's going to curve straight down. But no, it does continue forever this way. Think about this. Could you plug in the number 10? Could you plug in the number 10? Yes, you could. If you did plug in the number 10, it would give you the output -1024, right? So that means that if you go out to 10 and you go down -1024, it'll be on that blue line way down there somewhere off the screen. So you really can go to the left and to the right forever. So the domain really is x equals all real numbers. Now the range deals with the y values. Does any of this blue line exist at y equals 5? Up here. Does it exist at y equals 5? Does it exist at y equals 10? No. Does it at y equals 1? No. Does it even touch y equals 0? No, it doesn't, even though it looks like it's touching. I mean, when I draw it, it's touching. But we know that it just infinitely approaches but never actually touches. Does it exist at -1? Yes. Does it exist at -2? Yes. -4? Yes. -8? Yes. -10? Does it exist at -1,000? Yes. So it doesn't exist up here, but it does exist below the asymptote. Now, the asymptote is y equals k, which is y equals 0 in this case. So this blue graph exists below that k value of 0. So you're going to say the range is y is less than 0. And you can't say y is less than or equal to. You could only say y is less than 0. Okay, guys, this video is way too long, but let me just go back and let you know, or let's talk about how the original parent graph of y equals 2 to the x, how did it look like? It started off, it looked like at 0, and then it grew this way. From left to right, it grew. How about when you have a negative? If you have a negative in front of there, that's the one we just did right now. It has a negative in front of there. What happened? Instead of growing up, what happened? It grew down. That's right. It's an exponential growth function, but in a negative direction, right? An example of that in the real world is credit card debt. I've already said that, right? You get a bunch of credit cards, you don't owe any money, you start using all of them, your debt grows in a negative direction, right? Okay. So the A value affects whether it's opening up or if it's opening down, if it has a positive growth or a negative growth. It also affects on how fast it grows. So if your A value is half, now notice this is not negative, right? This is not negative. If it were negative, it's going to grow down, but this is not negative, it's positive. It's going to grow up, but because the A value is half, it's just going to grow a little bit slower. Okay? If the A value is 1/10, it's going to grow even slower, but it still grow. If the A value is 1/100, it's going to grow so slow, but at some point it will grow. Okay? So the A value does affect not only if it's opening up or down, but how fast it grows. What if the A value was 2 or 3 or 4 or 5? Then it grows really fast. It grows like really fast this way. Okay? So those are the deductions I would like you to make by you graphing each one of these. Let me just do one more. And let me do one right here. This is an interesting one because it does have an A value of 1/2, which is going to make it grow a little bit slower, but it is going to be a growth in a positive direction because it's positive. And it does have a K value of -3. So let's all go through this one as our final example, and then you guys could try to do some problems on your own. So the very first thing to do, and I believe it says that up here, whenever you have an exponential growth function with h and k, h is a value in the exponent with x, and k, the number that's being added or subtracted at the very end, ignore h and k and graph the parent graph but including the a value. Okay, so this is the meat and potatoes of today, guys. Please pay attention. What's your h value up here with x? Is there anything up here with x? No. So what's your h value? 0. Do you have a k value? Yes. What's your k value? -3. Right? Okay, so it'd be a good idea to start with that. H is 0. There is no number up there on the exponent with x. The k value is -3. Important details. Now, k is your up or down shift. After we graph the original, we're going to shift it 3 units down. That's what the k is telling us. I also know that the asymptote is the y equals -3 equation. But anyways, let's start with step 1, which says ignore h and k. So this is what I'm going to do. I always do this. I box in the function, but without the h, which should be up here, or without the k. I just focus in on this, and it's kind of like I ignore, let me put a box right here, I ignore the h and the k. All right? So I'm going to make an xy table. Everybody do this with me, please. I'm going to make an XY table, and I'm going to do consecutive integer inputs. Again, 0 in the middle, 1, 2, 3, 4, and in the opposite direction, -1, -2, -3, -4. It's very important that you don't skip any numbers, that it's in consecutive integer order. Because if it is in perfect order, then you're going to be able to use the perfect pattern on your answers. And that perfect pattern is going to be the growth factor of 2. So let's start with the easiest number. What's the easiest number? Plugging in 0. When I plug in 0 right in here, what's 2 to the 0? Well, that's 1, right? And what's 1/2 times 1? 1. And technically, that's the only real math you have to do. Wait, I'm sorry. It's not 1, it's 1/2. Does that make sense? Once again, let me show you. I plugged in 0 right here. 2 to the 0 is 1. And 1/2 times 1 is 1/2. And that's all the real math you have to do. I mean, you could, if you wanted to, plug in 1, do all that math. Plug in 2, do all that math. Plug in 3, do all that math. But the shortcut that I've been showing you over and over is to use the growth factor, the base, the B value. What is the growth factor? 2. So what do I do to this answer? I multiply it by 2. If it would have been a 3, I have to multiply it by 3 to get to this next output. Multiply it, but I'm multiplying by 2 because the growth factor is 2. So when I go 1/2 times 2, so 1/2 times 2 is 1, so that's how we get the next one. And 1 times 2 is 2, and 2 times 2 is 4, and 4 times 2 is 8. Do you guys see how easy that was, right? And going backwards, right? If this way you're multiplying by 2, then backwards would be multiplying by half. 8 times half is 4. 4 times half is 2. 2 times half is 1. 1 times half is half. Half times half is what? 1/4. Half times half is 1/4. What's 1/4 times half? 1/8. What's 1/8 times half? 1/16. 1/32. And you already know that it's approaching what? It's approaching 0. So let's graph this parent graph. This is called a parent graph. Let's graph it. Let's start with the coordinate 0 and half. 0 on the x, halfway up is right there. And then let's go to the coordinate 1, 1. If we go 1 on the x, 1 on the y, it's right there. If I go to 2, 2, and I'm talking about from the origin here, 2 on the x, 2 on the y, you'll get to right there. And then if I go to 3, 4, this next coordinate over here, 3, 4, 3 on the x, 4 on the y, it's right here. If I go to the last one, 4, 8, you're going to go 4 on the x, 8 on the y, it's up here. Now let's go in the negative direction, which we already know it's approaching 0, but let's do a couple anyway. -1 and 1/4. So from the 0, -1, and then 1/4 of the way up. That's half of half. Okay, so let's put a dot right there at 1/4 of the way up. And then the next one will be 1/8 of the way up. It's half of that. Then half of that, and half of the half, and half of the half. At some point, it just looks like you're drawing dots on the line, which you are, because you can't actually draw the fraction 1/32. That's too small. So there's our parent graph, and we know that it does infinitely approach 0. So you can put like an arrow right here, but don't draw the whole graph. Now the reason why we're not drawing the whole graph is because this guy has a k-shift of -3. This guy has a k-shift of -3. That means that I need to take all of these coordinates, all these dots, and move them where? 3 units down, because it's a -3. So on every single one of these, on this guy, I'm going to go down 1, 2, 3, and I'm going to put a dot right there. And then this next one, I'm going to go down 1, 2, 3, and put a dot right there. And the next one, down 1, 2, 3, put a dot there. The next one, down 1, 2, 3, put a dot there. Next one, down 1, 2, 3, and you're at that halfway point, at that 1/4, at that 1/8, 1/16, 1/32, and you end up with this blue line, which that's your real line. The original red one did not. That's your parent graph. That was focusing in on y equals a times b to the x. We ignored h and k. That was the red dots. So I always tell my students, put two x's on that red one, so I don't think that that's your answer, because that's not your answer. When you shift all of them 3 units down, that is your final answer. So on this one, yeah, let's draw an arrow, and let's put a line through all of these blue dots, and draw an arrow going up, because it does infinitely grow. It is a growth function. So the k value is either going to shift the original parent graph up or down. Again, the steps. Ignore h and k. I usually put a box around this. Do an xy table. Plug in an easy number 0. And then after that, you could plug in 1 and do all the math. You could plug in 2, do all the math to get the output 2. You could plug in 3, do all the math, get the output 4. But the easier thing to do is after plugging in 0 and getting out half, you could simply multiply the half by the growth factor of 2. So times 2, times 2, times 2, times 2. Backwards is dividing by 2 or multiplying by half. And that's how you get all your coordinates, and then shift them down 3 units at the very end. Why 3 units? Because the k value is -3. So I hope that makes sense right there. Now let's answer a couple of questions here on this red line, the actual graph. The domain. What's the domain, guys? You should know by now. X equals, does it go, remember the x's are left and right. Does it go to the left forever? Yes. Does it go to the right forever? Yes. Even though it curves up, it does continue to grow this way forever, right? So the domain, what do we say? X equals? All real numbers. You could use a symbol with that double-sticked R. Now the range are your y values, and y's up and down. So let me ask you this. Does this final graph, not the one with the x's, does the final graph, does it exist at -1, -2, -3? Does it exist at -5 or -10? It doesn't exist at -10 or -5, but it looks like it infinitely approaches the asymptote. And what's the asymptote? In case you forgot, the asymptote is y equals k. What is the k value? What is the k value? So what's the asymptote? Y equals -3. Y equals -3 is this line. I want to do it in green. It's this line right here. So our red line infinitely approaches that green line, but never actually touches. The asymptote is y equals -3. The range, where's this graph at? Is it above the asymptote or below the asymptote? It's above. So what is my range? It's going to be y is what? Y is what? Is it greater than or less than? It's greater than. What value is it greater than? It's greater than the asymptote. What's the asymptote? -3. So y is greater than -3. Y is greater than -3. And your y-intercept, that's just looking at your coordinates, setting x equal to 0, your y-intercept's half. So it does, oh no, I'm sorry. Your y-intercept for the actual graph, not the parent graph. This was a parent graph, I'm sorry. Once we're done with shifting the coordinates, you don't need this anymore, right? But your parent graph is the original. We scratched it out. Now we're focusing on this one. Let's find the y-intercept of this one. Where does it cross the y-axis? Here's 0. Here's -1, -2. Here's -2.5. So the y-intercept's -2.5. Or -2.5. That's your y-intercept. A lot of details, guys. I hope this video at least gets you familiar with what we're going to be doing next week. That's the goal. Now, if you kind of feel comfortable, on the second page on the back, especially if you have time left over in class, these are the 6 questions that I'm going to assign you on Tuesday. It's not homework over the weekend. This is homework for next week. But if you want to start trying it right now in class, the answers are posted on the wall on the homework board. Okay?